If you've ever struggled to set up a tensile test in Abaqus or wondered how to go beyond just a simple elastic model, this is the only tensile test masterclass you'll ever need. We'll kick things off with the basic, a simple elastic tensile test so you understand the fundamentals of stress-strain response in Abaqus. Then we'll set it up with a ductile damage modeling to capture material failure realistically. After that, we move into heavy hitters, Johnson-Cook tensile test using a cylindrical specimen, perfect for high strain rate and large plastic deformation problems. And finally, we'll finish strong with a welding tensile test where you'll see how welded zone respond under tension compared to the base metal. By the way, if you want to skip the simulations and get the files instantly, just check the description. Let's get into it. So without waste of any time, I would like to go and create the part. So the part should be 3D, deformable, solid, extrusion, and the approximate size of 200 for the global sketch. So let's go to the ASTM E8, which is the standard test methods for tensile testing of metallic materials. So if we scroll down, we see the sketch here, and today we're going to model the sub-size specimen. So I already did everything else, including the dimensions, so it should be 100 mm long and the width is 10 mm, and everything else I'm going to explain it very shortly. As this one has the symmetry, we are going to model half of this model and then mirroring the other side. So let's jump to it. Here we're going to create the very first part, which is the top part. This guy should be 10 mm and these two should be 30 mm. So the next thing to do is to create two parallel lines here, and the distance between them is 6 mm, but keep in mind their distance from either side is 2 mm. So we're good to create this one, and from this feature we can create the arc. So this is the arc here, and keep in mind you have to select this part first, then connect it to this part. If you do that, vice versa is not going to be right. The next thing we should do is to create a line in the center. So by creating the construction, we can create a line here which we are going to mirror our model on, and by left clicking on this one and selecting the mirror, we can copy our model to the other side, and here it says pick the mirror line, so we choose this line, and now it's time to select the entities by holding shift. We can select everything and click on done, and as you see we have our model, but before finishing the model we should put this number as 100, so everything is like the sketch we have. So we're good to go. By clicking the scroll button of the mouse, we can have the thickness of the sheet, let's say 1. There we go, the model is ready. So there's something else we should do. As you see here, there are a couple of lines that are not extruded through the model, so we should fix them by creating partition self-defined cutting plane. We can use 3 points, and by using these 3 points we can create a partition. As you see here, it goes through the model. By holding Ctrl Alt and left click we can rotate the sample, or we can use this one As you see, this line is extruded, so I'm going to do that for the other two. By doing the same thing, we are going to select this cell and 3 points, this point, and this point. So we have the partition here, and we are going to select this one, 3 points, this one, and this one. Then the last 3 points, which is this one, and this one. So the partition creation is done. As you see, these parts are now not going to cause any problem in the next steps. Next, it's time to go to the property. From create material, we create a material named steel, and from elasticity elastic, we use the Young modulus of 210,000 and Poisson's ratio of 0.33. So we just going to simulate a very simple elastic tensile specimen. We don't have plastic in this video, but in the next one we are going to have the plasticity. And from here we should create a section, solid homogeneous. The material is steel, and we have to assign the section. Now it turns green, and it means the section is assigned. So we can go to assembly and assembling our model. It should be independent. Click OK. What I'm going to do now is to translate the instance. So I'm selecting this instance, click done, and select this point and translating it to the center of the coordinate and click OK. So by doing this, I can create the coordinates of the reference point and everything else way easier. The next thing to do is to go to the tools and reference point. So this point is 0, 0, 0, and this point is 0, 100, 0. So I want to create a reference point in 0, 100, let's say 120, and negative 0.4, which is in the middle of this edge. And if I click OK, I see that the reference point is created. If we want to change the coordinates, we can go from the assembly here and features, reference point. So here is 120, we can change it to 110 and we click OK. So if you ever wrote down the coordinates wrong, you can fix it really easily. So we go to the next one, which is step. We create a step of static general, and we click on this one. This one should be 100,000, 0.01, 1e minus 9, 0.1, and OK. This step is done, and we can go to the interaction. Here, by selecting create constraint, I'm going to use the coupling. By clicking continue, we select the reference point, and the surface we're going to select this surface and coupling it to the reference point, and OK. So this reference point is representing this whole region. From the load, I'm going to create some boundary conditions. So the first one to do is to go to the symmetry or encast and choosing this side and encast. I have to move it to the left, so this is the initial condition until the final time of this step 1. And we create another one which is displacement in rotation, and we select this reference point. We put all the values 0, move left, and this one should be 0.8 in the step 1. So here we have we constrained all of the degrees of freedom of this part, this part, the upper one, in the first step, and in the second one it can have a displacement of 0.8 millimeter in the step 1. So the load is done. We go to the mesh, we mesh the part, and the mesh is not bad for this analysis, and we're good to go to the job. So we create a job and name it Tensile. Continue, OK, and submit the job. Let's monitor the job. As you see, the job is completed. Now we can go and visualize the results. So here is the animation, and it is displaced in the y direction for 0.8 millimeter. Now we can plot the stress strain curve for this one, and from that we can calculate the elastic modulus. Now from the ODB field output we can go to this one. The position should be unique nodal, and from the node sets we can use the constraint reference point, and from the variables we can select U2 and RF2, and we can have a plot, and from XY operate on XY data and combine. We use this one and this one, then we can plot it. So here it is, the force versus displacement in the elastic region, and you can copy the data, or even you can from here you can select the stress or strain. So the strain should be here. So we can have a stress strain. If we double click on it, it should be, the stress should be this one, but it doesn't matter. You can work on your data if you want. And that's everything. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. Hey everyone, welcome back. In this tutorial we are going to simulate a tensile test using damage for ductile material. So we kick off with creating part. it should be 3D deformable solid extrusion and with the approximate size of 200. We're going to do the same modeling as the previous video, which was the ASTM E8 sub size. So this guy should be 10 and these two should be 30. Now we have to create two lines like this and a line like this. The distance between them should be 6 millimeter and each of them should be 2 millimeter away from the side. So yeah, that's cool. And we should create an arc like this and this, and also we are going to have them 12.5. Alright, cool. Now we have to create a construction line which we are going to do the symmetry on. So by left clicking on this one and holding, we can go for mirroring. We want to copy, we pick the mirror line and we choose all instances, and as you see here we have our model mirrored. This one should be 100. So yeah, that's okay. Now we want to use the depth, which is the thickness of the material. For this case is 2, and these lines should be extruded through the material, so we use the define cutting plane, 3 points, this point, and this point. We can create the partition. We're going to do the same thing for this part again. This one, I'm clicking the scroll button of the mouse. So yeah, I'm doing it faster because we did all these things in the previous video. So we have our part created. Now we can go to the property. We are going to create the property for the material. We name it steel. From general we use the value of density. Here we have the value of the density and the unit is ton over millimeter cubic. In the mechanical elasticity, elastic 210,000 and Poisson's ratio of 0.33. Now it's time to go for plastic. We have these values. Now here let me talk about this part. So the first value of the yield stress is actually the yield strength, and the last one is the UTS, which is this part, sigma y0. And if we are going to use the simulation without the ductile damage, the curve would goes like the dash line, but we want to use a failure damage so that we can have a more realistic simulation. So we have to go in the mechanical damage for ductile material and ductile damage. Here we have a couple of fields that should be filled. So this one 0.35, 0.33, 0, and also we have to have the damage evolution, displacement, linear maximum, and 0.4. We click OK. Now we have to create a section, homogeneous, and the material is steel. Now we want to assign the section. I would like to uncheck this one. Okay, now it turns green, and the material is assigned to the part. Now we're good to go for the assembly, create instance and independent mesh. It's better to move the instance to this point because we are going to create a reference point and it's easier to follow. So from tools we go to the reference point and we use the value of 0, 100 and 10 and minus 0.4. Minus 0.4 is because we are going to opposite direction of the Z. So the reference point is created. Now we can create a set. The set manager create and let's say RP, and we select this RP reference point and we have the set. Now let's go to the step. The step this time should be dynamic explicit. From the master scaling we use scaling definition below, create, and here we put the value of 1e minus 4 and we uncheck this scale by factor and OK. One important step is here to go to the field output, and from state we use the status because we are going to simulate like the rupture here in the middle of this part. We want to see that, so we click on status in order to see that. And the next thing to do is to go to the history output. We double click on this one. We use set RP, evenly spaced time intervals of 200. And we use U2 and RF2. We want to make sure that it's correct, yeah. So this step is done. Now we have to go to the interaction and create a constraint of coupling, choosing the reference point, node region, clicking this part and OK. Now this part is coupled to the reference point. Now it's time to go to the load. Okay, then we go to the boundary condition manager, create. First we use the symmetry and encast to encast the lower bottom part. Move to the left. Now create one from displacement type. We select the RP point. We select all of this and we click OK. Move to the left, but this one keep in mind we have to create an amplitude. So we say create an amplitude, tabular, and I can use this one. I can copy here and Control C, Control V. From here we use the amplitude too I created. So dismiss. Now we can go to the mesh. Here from seed part I put this value on 1 mesh and we have the mesh. Also we want to check the element types. So from here it should be 3D stress, explicit. We uncheck this reduce integration and I think it's okay. Now we're good to go to the job. Here, let's say tensile ductile damage. So we click OK, and from the job manager I would submit it. Now the job is completed. We can go to the results. Okay, from the plot contour we can contour the plot, see how the damage happens. Here we can make it slower, or we can go manually like this, and we see here like the fracture happens. Let me switch to this part. Yeah, and the part is torn apart. And the thing about the status I told you about is to see this one. If you haven't checked the status in the field output variable, you are not able to see this one. Okay, so let's go to the ODB history output and choose this two and plot. We have the plot here. From the create XY data, let's go to the operate on XY data, and we can use combine here, U2, RF2, and plot the expressions. So here we see that it is start here linearly, and we had like the damage started from here and it went to the 6 millimeter of displacement. What we can do right now is to go from here XY data plot and edit, and we select the first one, and by holding shift we can choose all of them and copy. Let's have them on Excel file. Here we can paste it. This one was this placement, this one was the force. So to calculate the stresses and strain, first we're going to have strain here and stress. For here we have to divide the displacement by the gauge length, which is 25. Let me show you here. And this one, the gauge length is here 25. So we double click on this one. Now we calculated the strain. Now to calculate the stress, we have to divide the force by the area. So 6 millimeter times 2 millimeter, which is the width, the thickness, and we have the stress here. So as you see, this one, the width is 6 millimeter and the thickness was 2 millimeter. So here we have a stress and strain. We can calculate this, and there we go. Alright, that's it. I hope you enjoyed the video, and if you did, please like this video and subscribe to the channel. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. In this Abaqus tutorial, you'll discover how to accurately simulate the tensile fracture of a steel specimen with a circular cross-section using powerful Johnson-Cook damage model for the first time. But here's the interesting part. Can this simulation really match a real tensile test? Stick around until the end where I'll show you exactly how to convert your Abaqus force displacement results into stress-strain curves so you can compare your simulation directly to a real-world experiment or use that as an input for your Abaqus simulations. Let's jump right to it. Now open Abaqus, create part. As we only have one part, I don't mind renaming it. Deformable solid but revolution. It can be 300. Continue. The part we're going to create is based on the ASTM E8. We have everything required here in this standard. I already created the sketch. You can see that here this should be 15, 20 and 64, 39. Everything we need is here. So let's go create it. Here I need to create lines, so I create two lines just like this. Now this should be 15 and this should be 20. Now we need to create another line somewhere around here. Scroll button. The distance should be 625 here, so let's create the arc. Here you need to select this one first, because if you select this one, let's see what happens. The arc is not what we want, so undo, select this one, and we have the arc. Let's add the dimensions of 10. Okay, 10 is good. Now this one can be somewhere around like 25. Now let's create a construction line with this tool. We create a construction line because we want to mirror everything here. Left click and hold and go to the mirror here. And it says, do you want to copy or move? We want to copy. Select the mirror line. Now we select everything here. We don't select this construction line and done. As you see here, we have the model. Now let's delete this dimension here and set a new value for this one, 64, 39, and we have this value here. Now we need to close this part, because if we don't, let's see, if we want to remove this, it says the section must be closed. So we need to close this one. It also indicated which part is not closed. And done. Because we have two construction lines, it also requires to select the construction line. We select this one and we want to rotate it along this one, 360, and done. Now the part is created successfully. Let's go to the property. From property, we create the material properties here. This is steel, general density, as it is millimetric. This should be 7.8 E-9. Mechanical elasticity and elastic, 210,000. 0.3. From mechanical, we go to plasticity and plastic. But we don't want it to be isotropic. Instead, we want it to be Johnson-Cook. About this one, if we go to this PowerPoint, Johnson-Cook plasticity model, as you see, describe the flow stress of ductile materials, strain rate effects, and temperature sensitivity. According to this formula, this one is the flow stress, and the parameters here are described here. For instance, A is the yield stress, like the one we had before. B is the strain hardening, and N is the strain hardening exponent, while the E.0 is the strain rate as a reference. You can also read about it yourself, but this is the summary of the material properties we have. Then we go to Excel file. I have it ready here. Just need to hit the Control C and Control V here in order to have the yield stress and everything else. Now from the mechanical damage for ductile materials, instead of ductile damage, we use Johnson-Cook damage. Then we have the parameters here. I need to explain them a little. So according to the Johnson-Cook model, when the ductile metals begin to fail, we do have nucleation growth and the coalescence of the voids. According to this formula, we have the strain, and we have other parameters, damage parameters such as D1, D2 to D5, and our fitting parameters according to the experimental. We don't need D5 here because it relates it to the temperature. We don't have the temperature here, so we ignore this one. And we do have the damage accumulation, and this parameter omega indicates the damage parameter, and as we reach the value of 1, the material begins to fail. It's similar to damage for ductile materials where we define the D as a damage criteria, but this one is a little more complicated. So let's jump back to the Excel file to copy everything else here. Control C and Control V. We need to input the damage evolution. We have the displacement of 0.44 and OK. Everything is done here. Then we click OK. Now we need to create a section 1 solid homogeneous, and OK. Then we need to assign this section to this one. As always, we uncheck this one because we don't want to have too many sets. And OK, let's go to the assembly and assemble the model. We need to translate it. So from here, we need to select this one, this tiny point, and we can put it here. Scroll button, and we have it. From tools, reference point, we need to create a reference point just right here. And we're done with the assembly. We can go to step, create a step 1 initial, and it needs to be dynamic explicit. From here we go to the mass scaling, use the scaling definitions below, and create 1E -4, and we uncheck this one. OK, but it's not over. We need to go to the field output manager and click edit. Here from state we need to check status, otherwise we don't see the failure even if it occurs. So OK, we're done with this step and we can go to the interaction. Now one thing we need to do is to couple this part to this reference point. For that purpose we go to create constraint and coupling, continue, select the reference point, and done. It needs to be a node region. We select this one, done, and click OK. Now as you see, it is coupled to this reference point. Now let's go to the mesh. If we go to the part, we see that it is orangish. It means we cannot mesh it in a structured way, but we need to create some partitioning. I click on this one, point and normal. Let's select this one and this one, and as you see it turned yellow. It means we can have a sweep mesh. Here we need to select this point here, done, point normal. Let's select this one and this line and create partition. As you see, the whole model turned yellow. It means we can mesh it. So if we go to assign mesh control and select everything and done, you see we can have a sweep meshing. We can have it hex. Okay, we can mesh it sweep. That's okay. I would like to put this value on 2 and mesh the model. As you see, the model is meshed. Let's go and check the property. As you see, the material property is intact. Okay, let's go to the loading and boundary condition. Now from boundary condition manager, create, Step initial, symmetry, continue. Then let's put this one on cells, and we select this part, done, encast, and okay, the bottom part is encast. Now create another one, displacement and rotation, continue, select this one on all, and let's select this RP point. We close it in every direction in the initial, but in the second one, let's put this one on 28, but we need to select an amplitude. So tabular is okay, continue. I already have it on my Excel file. Control C or copy, then we can paste it here. This is the amplitude, but we need to select it, amplitude 1, and OK. Now that's it for the load and boundary condition. We already had the mesh, but we need to go to the part, assign element type, select everything, done. Make sure to uncheck this one, as we are going to have a failure. We need an accurate simulation, so uncheck this one and put the values on dynamic explicit. And let's go to submit the job. So create job 1, JC Tensile test, continue. Okay, we can submit the job. Let's monitor it. Everything looks fine. Before the job is completed, I want to ask you a favor. If you enjoyed this video so far, please leave me a comment down below. It's completely free for you, but it motivates me to create more Abaqus videos for you. The job takes a while, but I pause the video here and we'll be back after the job is completed. Okay, now the job is completed. Let's go to see the results. This is the final result, but let's put it back just right here. And from the animation control, we can make it a little slower. Okay, now let's see the animation first. Okay, I'm gonna stop it just right here. And as you see, so there's a fracture here, apparently a ductile fracture. Let's have the force versus displacement. Okay, from here we go to ODB field output, continue, put this on unique nodal, and here RF2 and U2, and from elemental nodes we select the reference point and we plot it. This is the plot, but we need to have displacement versus force. So let's go to XY data once more, operate on XY data, continue, and here select combine, double click on U2, then double click on RF2 and plot the expression. Here, as you see, first we have the linear part, which is the elastic part, perfectly linear. Then we have the yield stress here, and after that we have the damage, and after the damage we have this line. If we don't have the damage criteria, we don't see the drop in the curve. So it's vital to have the damage criteria. If you want to extract the values, we can go to the XY data, temp1, which is the temporary one, click on edit and select the first one, hold shift, the last one, and copy. Then you can go to an Excel file, paste it just right here. So let's say displacement, and this one is force, and you can plot it. We can also convert it to strain and stress. So let's say strain, and here is stress. You need to define the value of the displacement by the gauge length. The gauge length was 50 according to the standard, and we have this one. This is the strain, and for the stress we need to divide this one by pi, which is 3.14 times d D2, which is 12.5 to the power of 2. This is the stress converted. Now we can plot the stress strain curve, which is similar to the force displacement, but the values are different, and you see here the curve is more accurate in terms of seeing the stress and strain. You can also calculate the yield stress and do whatever you want with the data. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any questions, just ask me in the comments down below. I respond to every single one. Thank you. In our previous videos, we explored the tensile behavior of a base metal using Abaqus. Now, in this tutorial, we take it a step further by introducing a weld into the model. How does the presence of a weld affect the stress distribution, deformation, and failure mode? Let's walk through the full simulation process from model setup to post-processing analysis. Are you ready? Let's start. By the way, if you want to skip this tutorial and get the files instantly, just watch the pinned comment down below for the direct link. Let's start with creating part. Create part, 3D deformable solid extrusion, continue. Now we need to create a bunch of lines like this. And from here I want to add a constraint and equal length. These two, select these two, and done. Now I don't need to assign the dimensions for each of them. Now this one should be 10, and if I put this value on 30, you see the other one changes as well. Then we need to create two lines like this and like this. The distance between the two must be 6 millimeters, but we need to select this value at 2. The other one must be 2 as well, so I press escape. Then we need to create arc here. Select this one first, then the other one. It's the same for the other one, and that's it. Now we need to apply the equal length once more on these two. Then here 12.5. Then it's time to create a construction line from here to here. Now we have a line and we want to mirror this side to the other side. So left click and hold on this one and select mirror. First we need to say copy, and we select the mirror line and we select everything, done, and boom, we have our model. Let's put this value here on 100, and that's it. Now done. The depth can be 1. And we have this material here. Now we need to create some modifications. First of all, we need to create the weld. From here, partition face sketch, select this one, done. Then we select this one, and here in the middle we need to create a line like this and a line like this. So create one construction line here in order to make the symmetry. Here let's say 1.5 for this one and 1.5 for this one. Now we have the weld. Let's create that, and that's it. Yeah, the weld is in the middle. Now we need to extrude them through the thickness. So left click and hold on this one and select partition cell sweep. Select this line first, done, and sweep along edge. You select this edge and create the part, and as you see the part is created. Now we have to do that for the other one. Select this one, done, sweep along edge, and we can select this edge and create, and let's do that for this one first. Done. This one, done. Sweep along edge. We can select this one and create. Now it's time for the last one here. Done. Select this one, done. Sweep along edge, and we select this edge and create partition. Now let's do it for the weld. Select this one, done. This one, and done. Sweep along edge. We can select this edge. We can select this edge and create part. This one. Then we select the line. Done. Sweep along edge and this edge, and it is created. Now if we want to rotate the samples, we see we have the weld on the other side, we have other lines, and that's okay. Now let's go to the materials properties. To download the materials properties, let's go to the femaster.com. Then from shop, go to the material property packs and select this one, add to cart. Then go to the checkout, fill everything and place the order. It's totally free. Once the order was completed, you can download this one, and I want to open this. Here we have a base metal and a weld metal materials properties. Let's start with the base metal first. So from here we go create material properties. Let's name it the base metal or BM. We need the general density, elasticity and elastic. We need plasticity and plastic. We need also damage for ductile materials here, and that's all, I think. Let's go to this file. We just hit the Control C and Control V here. For the elastic, we go here, copy and paste. For the plastic, we need to select this one and paste. And for the ductile damage, we have this one. Then we need to go to sub option and damage evolution. This should be on displacement, linear, and the value was 0.44. And okay. Then okay, now we have the base metal. It's better to copy the base metal and name it weld. Then we edit this. The density and the elastic modulus are the same, and the damage evolution is different, so that's plastic properties. Delete these rows, and let's go to the weld metal here and copy this one. Then we go here, simply paste it. Then we need to go to the damage evolution. This one is 42, so we can copy this one and we just paste it here. Then we need to go to the damage evolution, and this value is 0.55. And we have the ductile damage, we have the density, plastic and elastic. Then okay, we have a base metal and a weld metal. Let's create the section. So create section here. We can name this BM or base metal solid homogeneous, continue, and we need to select the base metal and okay. Now we need to create another section. We name it weld solid homogeneous, continue, and we select weld and okay. Now we need to assign the sections. I uncheck this one in order not to create too many sets, and I select this one, then hold shift and select this one, then done. We need to select base metal for them and okay. And we have this part without the section, so I select it and done. It should be weld and done. If you want to see the differences between the materials properties, or if you want to make sure that it's right, you have to go to here. Instead of property defaults, Let's put this on materials. It shows that there are two different materials. If you want, you can change the colors. For instance, you can put red for this, and as you see, this one is red and this one is green. So I would like to put that on property defaults, and we need to go to the assembly. Here we can assemble the model. Part 1, it can be independent as we only have just one part. Translate from here to here and done. Let's reset the view. Then we need to go to the step. We need to create a step. Step 1 initial must be dynamic explicit. Continue. NLGeom must be on, and we go straight to the mass scaling. Here we need to use the scaling definitions below and create. Here check this one and put the value of 1e minus 4 and uncheck this one and done. Now this is the scaling and done. Another important thing to do is to go to the field output manager, double click on this one, come here to the state and check the status. If you don't check the status, you won't see the separation or fracture visually. So click on OK, dismiss. Now we're done with this step. Let's go to the interaction. Okay, in the interaction, we need to go to the tools and reference point to create a reference point. Let's select this one to create a RP, and from here go to the create constraint and select coupling. Continue. You need to select the reference point first, then done, and we need to select the node region. You select this part and done everything and OK. As you see, this is coupled to the reference point, and now we're done with the interaction. Let's go to the load. Here we need to create the boundary condition. Create first one in the step initial, continue, and select this part and done in CAS and OK. As you see, it is applied. Now go to the create. This one we need to create one from displacement and rotation and continue, select RP point and done. Now check everything because it is the step initial, but we need to modify that into step 1, and the U2 can only displace 15 millimeters. Now we're not done yet. We need to create an amplitude, otherwise there would be a problem and it won't let us complete that. And as you see here, if I click on OK, it's a in explicit analysis we need to create an amplitude. So let's click on this one, check tabular and continue. So you need to create one. This is 0, 0, press enter, 0.1, 0.1, 0.2, 0.2, and we go just like this. You can press enter every time. And 1, 1, and that's the amplitude. Then click on OK. Now you need to select the amplitude, then OK. Now we're done with the load and boundary condition. Let's go to the mesh. Here in the mesh, as we selected the part independent, now we can create mesh easily. So mesh part and select, and as you see, the mesh is created. It can be better, but this is just a simple example and it has an educational purpose. So to further refine that, let's put that on 1, delete mesh and mesh it once more. Now it's better. Let's go to the job to create the job. But before creating a job, I want to ask you a favor. If you enjoyed this video so far, please drop me a comment down below. It's totally free for you, but it helps me grow and motivates me to create more contents like this. Let's go and create a job. I would like to select and create job manager. So We can name it tensile test weld and continue. Okay, now that here we can submit the job easily. Let's monitor this, make sure there's no error. Just ignore the warnings, they're fine. And as you see here, it says it is completed successfully, so we have to wait till the job completes. And the job is completed. Now let's go and take a look at the results. This is the result of the final state. Now if we select this one, and if we go to the option, viewport and annotation option, let's set all off, just keep the legend and OK. Now here from option and comment, we need to put this on feature edges. It is better. Now for the animation, let's put this on here and let's take a look at the animation. And as you see here is the weld. After the part subject to the tensile test, the weld remained intact. It means the weld parameters were selected in a good way so that it has a better strength and the part is ruptured from non-welded part, which is totally fine. Right now let's go to the XY data, create XY data from ODB field output, continue, and let's put this one on unique nodal. And from here we can have U2 and we can have RF2. Here we need to select the reference point. Here we can select it and plot this. This is the plot. Let's modify that. So once more we go to the create XY data, but this one we would like to operate on XY data and continue. Then we go to the combine. Let's select the U2, then RF2, and we need to plot the expression. Now you have the force versus displacement. It goes up, then elongates for like 5 millimeters, then drops down. A typical force displacement curve. You can also change this one to stress and strain, but you have to do that manually. In the previous videos we explained them completely, but here from here XY data you can right click and edit, and you can select all of the data and you can copy and paste it in an Excel file. So make sure to see the previous video to know how to do that. And that's it. Thanks for watching. If you found this helpful, please smash the like button and subscribe to the channel to see more videos like this. Don't forget to watch the video on screen before it ends. Stay tuned.